Yes.
Can you see me? Yes.
Let me try. Okay, yeah. So thank you very much. I'm sorry that I was unable to go to the conference because the procedure is too complicated. So I'm excited to give a Skype talk. Okay, so the talk title today, I try to explain some topology in combinatorics and data science. Okay. The one, I think the first part will be more mathematical. So this is what we call this what we call a chromatic space and some connections with components. Well, I would say a bit more why when I talk this one. Okay. Now also I explain more for some applied topology, because nowadays actually Morse theory actually is very active in the applied topology. Okay. So let's say here, so I think to my understanding, like Morse theory is now actually becoming, of course, it's very powerful tool, not just mathematics, and it seems also very important in application. Right? So we are considering the mathematics, and I would say that try to see one topic related to configuration space. So we get some extensions of the notion of configuration space to so-called chromatic space. And there's a lot of work done, which is important work done of the solid applications of Morse theory to configuration space. And of course here we just talk about the notion of the chromatic space, and hope there will be some application of Morse theory as well. And also this some discrete Morse theory will be useful in application, so we explain some extension of some notions. Actually, we try to explain some kind of simplicial homology extension of the simplicial homology to hypergraphs. So I hope to get some applications. Okay, so now let me start to explain the chromatic space. So let's go back to the basic things in graph theory. Okay, so when you view so graph here, I make only the simple graph. Now talk about these people in graph theory, right? Talk about these coloring of graph. So the coloring means just put colors on the vertices. So there's one law is that if there are two vertices joined by one edge, we should have like different colors. Right? So that's the rule for coloring. So mathematically, I think the color K coloring should be, the definition will be like is a function, right? For the set of the graph G to some numbers 1 to K. Now there's a law is that if two vertices A, B joined by edge in the graph, then the value of that A and that B are different. I think that's the correct, should be a correct understanding for color. Okay. Now, I just review the chromatic polynomial definition, right? And this is definition, I think people denote by PG of T. So it's a number of T colorings, right, on the graph G. Okay. Now, by means of polynomial, I just want some argument to say that PG of T is really a polynomial, depends on the T, right? Okay, so it's here's some few examples. Well, like that PG of 3, like this example will be given by values 12, right? And there's 4 colors theorem should be states.
So the connection is lost.
Right. Okay. We. Okay, so now I'm talking about the definition of chromatic space. Okay, so let's think about just still start with it. G is a graph. Okay, so the vertex set, let's say labeled by 1 up to n. Okay, now and second vertex 2 with color x2 and so on and so on. So we put the colors here. Now according to the rule, the vertex I and the vertex J, let's say if it's 8, then the color xi, xj should be different. Now the point is that now we just choose this.
No, the problem is that I share internet from my
Because
phone.
this construction at the topological space, right? This is the space, subspace of the n-fold Cartesian product. So if you look at the definition, right? Suppose that G is the complete graph, right? With vertices 1 labeled by 1, 2 up to n. This is just usual computation space. So we can think about this as an extension of the configuration space. I think some people have been called this like a graphical configuration space, and but it may be confused with a notion of a configuration space on graphs. So we just choose as like different name for chromatic space. But anyway, so this is something actually some interesting construction in topology, right? So the rule is very simple. I just say that if there's 8 joined by 2 coordinates, then we these 2 coordinates xl, xj are distinct. Okay, so now before we see that, actually there's some interesting connections between combinatorics. Okay, so first thing, let's try to see what happens if because we have a space now. Okay, so this is a chromatic space. Okay, so we have a topological space, and then we try to compute the only number. Okay, just do the beginning. Okay. So, well, the interesting point is that so you give a graph G. Okay, so I just look at the topological space. Okay, so and then we do the order number. This is the left-hand side. Now you look at the right-hand side. Okay. So there's as we say, there's the chromatic polynomial of the graph G. This is really just come from this graph scheme. And then the interesting polynomial side. Okay, so now we put the value. M is a compact triangulated homological manifold, right? Okay, so now we just assume the only number to be positive. So now this is some number. So insert this number. Okay, so change t to this value, okay, and then it comes out they are equal. Right? So this will get some interesting equality between like all the numbers for space and the value of this geometric polynomial. But after this, there was I mentioned this is Junda Chen is actually a young guy. A few years ago, when he was in master thesis, he tried to work on this question based on the early time. There's some work done by Eastwood and Archie on the case M is a complex projective space, so then extend. And then they thought this topic will be kind of interesting, so we moved further. And actually, this young person is keep working. Next person, next one tried to compute what's going on for Polynomial series of the space. Again, so we get the chromatic space. Okay, so now let's test in the case that I simply just take the Euclidean space. Okay, so let's start with the easy one. So let's make it the easier one. So just take more true homology. Okay, so actually they look at some ring structure, and this ring structure you will algebraically get geometrical rings constructed divide the purely algebraic. Now, the part of the interesting part is that to compute actually this should be Polynomial Hilbert series. So I think that Volodymyr we call Polynomial series, or other people call it Hilbert series. Now, well, let's do this. This is the Polynomial series, and on this side you put the H, so you just say Hilbert series. Okay. So now we get a ring. So this is the graded algebra. Okay. So now you're counting the dimension for the degree k. Okay. Now put it t to k. So same definition. Sum up, and then the way of this computer, this ring algebraic part and topology part is Polynomial series. Well, I think that this is also was done a few years ago in Junda Chen's thesis. It's a nice young guy, but actually he did not realize that this was one of the very classical theorems given by the Solomon in his actually famous result in the area for the hypergraph algorithm. Now, the method is different, but there's some essential in the result will be restated. But anyway, so this is because for the special cases. So then they come to the question, right? Because now we are trying to work on the more generalized configuration space, where we call it the geometric space, right? So we try to see whether we can push further, say to general manifolds, and then I think we can get some good result. Okay, so the result will be like that. So this will be the new result. We got just state here. I think we are finishing the paper to finalize the paper. Right. So essentially, one of this theorem will be like this. Okay, so suppose that M is a manifold. Okay, and we need a little bit or need some hypothesis. So the M can be written as a manifold, manifold N times R. Okay, so we shape this vector R over here, the numbers here. And then, so here we assume like the dimension of the manifold M is M. And assume like the size of vertex set of the graph G is the cardinal of the vertex set of graph G is n. Okay. And then we can get let's try to compute the Polynomial polynomial. Okay. So this is the Chromatic Space for for this manifold n. Okay, so now we compute the polynomial on this side. Okay, so now the right hand side, actually, you will get start with n, then you can compute the polynomial of n. Okay, so this is just whatever something polynomial, and okay, so determined by the manifold n. Okay, so variable is t, and divided by some t to the n minus 1, and insert this geometric polynomial. Okay, then multiple by another term minus 1 t to the n minus 1 to n, and then comes out to be the quantity. Okay, so so in other words, we actually get some connections between the polynomial of this chromatic space and chromatic polynomial of graph, right? In such a way, one to another, together, and for more general cases. Next will be, I guess, is our new result. If you come to be we're happy because and because when people look at the hypergraph arrangement, and if you look at the Euclidean space, we have a lot of tools, combinatorial tools. You can determine the homology, the co-homology. Now we move to this general manifold, and we have a topological method to determine this co-homology, and then we can get some information on the polynomial. Okay. So I just mentioned a bit more. Okay, so in this case, okay, in our case, for n to be already the manifold times r. Okay, so you see that we have the geometric space. That means the coordinate of this tube n2 or point, and the coordinated part of it. Some of them are not equal. It means I coordinate I and j are distinct if they have there's A joined by a graph G, right? Now there's always a subspace, so you have got the usual configuration space, means all xi and xj different if I is not equal to j, that means there's all coordinates are distinct. So the usual configuration space will be subspace of the geometric space. Then it will induce a group homomorphism from the cohomology of the geometric space to the cohomology of the configuration space. Now the theorem is that this group homomorphism actually is a monomorphism, so it's injected here. Now on the right hand side, actually there's a work done by Dragomanov and Euler a number of years. I forgot how many years. Many years ago, they did some one classical work. They did is that the cohomology ring of this one actually is known. So this will be certainly we can describe the cohomology ring of the geometric space as a sub-element of this cohomology ring of like Cohen-Taylor algebra given by this way. So now, next, I'll try to explain a little bit on the ideas. Actually, I found this construction is very interesting because the other tool, I just mentioned a key tool that we actually study is kind of object. Now, there's one thing is not very good on the chromatic space is that for usual configuration space, we have like these coordinate projections with the final bundle. Also, there is a bundle configuration structure that helps to compute the homology, in which always we have a scrap sequence can compute, and then you can determine the homological properties using these vibrations. Now, for general chromatic space, this vibration may not work. So, but on the other hand, if you think about the graph theory, okay, so something related to this chromatic polynomials, people they use people in graph theory. They look into these polynomials. They always have to look at say Deletion-Retraction rules for graphs. So basically, delete one edge and growing two vertices on this one. So I use this forward notation for graphs. So you remove the edge, and then this means that the two ending vertices of the F will gluing together as one vertex, but we take away this, forget this edge F. Right? So this will be like a kind of inductive way to go to general graph G. And well, there's a nice geometric property that if you look at this one, so look at the geometric space, okay, so assume for graph G, and then you forget is the HF. Well, you forget the HF, that means you allow, say for example, the F is H joined by the vertex, say labeled by 1 and 5, right? So in the geometric space F and G, that means that coordinate 1 and coordinate 5 should not be equal. Okay, they are distinct. But then if you remove it, that means you allow coordinate 1 and coordinate 5. They can allow equal, okay, so that we get a bigger space. Now you look at the co-fiber. Okay? So essentially you look at because of subspace, so you look at equivalent input and you look at the construction of the and then it comes out you can determine the Thom space of the chromatic space. Okay, so by growing this with HF, and so we got another graph which has like this H with the F take away, but the growing ending vertices of F together, but get a graph this one. So we get a nice two-fiber sequence, and that certainly, as we learned, I think when we observe this two-fiber sequence, we already see that there is like a topological way to approach the homology, right? Because each step, say when I do like deletion-retraction law for applying for one edge, actually the full fiber sequence, that means I have a long exact sequence. So it will be for general, and of course we will make a step sequence to approach to that. But this really what I talk why I assume M to be the manifold M to be like n times R. I just take an easier case, so that is which one? Yeah, the homology, cohomology of this one will be the sum of these two. So with long exact sequence, but short exact sequence, eventually you can run out like in this Fourier series can be just got it. Right? And there's some more general result actually can got it. Okay. So yeah, I think this is the part like I like to explain to you on the mathematical part. There will be interesting like the extension of configuration space, right? And it has some nice connections with combinatorics. And as I mentioned in the beginning, like Morse theory actually can apply to usual configuration space. I think it can apply to these kind of objects as well. Maybe have some interesting thing can be discovered when we try to explore. Now I guess I move to next. Okay, so now let's say a bit on the applications applied. Okay, so this one is try to extend the notion of simplicial homology to the kind of homology in the hypergraph or hypergraph. Okay. So hypergraph people actually look a lot, particularly like for the social network or whatever they have some. They like to look at this like hypergraph. Here's a typical template. What do they call like a collaboration relations? Like so they try to study the relationship of collaborations, like this course of the papers, like ABC. It's possible like ABC have a course of the paper, AB has, AC has, but BC does not have a course of the paper, and AB maybe have some own paper, C maybe have no own paper. So this kind of things give some information like which is hypergraph, but not abstract simplicial complex. Okay. So then the people will ask whether we can still produce homology theory on hypergraph. So that's what we can try. Actually, the question is asked Stephen Bresner, he's a computer scientist. He interested on hypergraph, and when he likes the topology, and he heard people talk about a lot of like homology theory, he asked whether we can also produce a homology theory, hypergraph. So that's the case. Actually, I mentioned answer we actually get yes. Okay. So I just say a little bit ideas. How can we do? Okay. So first of all, start from the hypergraph. Of course, we can get the abstract simplicial complex. Well, just by like getting back or missing phases. For hypergraph, now you talk about simplicial complex. That's not an object. But it's okay. Let's ask it to be patient a little bit. Okay. So that means what? For simplicial complex, we have a chain complex already. Okay, usual one. Okay, so simplicial complex, we just close down. So we have chain complex. Now we look at the rule of there is a linear combination of elements in the hypergraph. So this is a graded subgraph. So in each level we get graded subgraph of the chain complex. But this itself, the H itself may not be a chain complex. Now what we can do in mathematics? Well, look at this graded subgraph inside the chain complex. We'll move down. Take the smallest chain complex containing these graded subgraph. Okay, so that's one way. So what we call it is super stuff. Okay, so let's like just move down. And on the other hand, 0 is it's of course in chain complex below. Okay, so then move up to take the graded largest subchain complex that contained in CH. Okay, so we get two of these one. One's chromatic. Okay, so do that. And then comes out very interesting in observation is that well, the homology, okay, so we have a nice curve. So this is the lower bound and upper bound. They are induces isomorphism of homology. Oh, then we have to try to get a natural notion for the homology of the hypergraph. That's important. So that's what we call this called invented homology of hypergraph. So let's so now see we try to study the hypergraph. We look at this guy. And this is the chain complex. Now the inclusion induces this is the middle one is not chain complex. Now this is the isomorphism of homology. So if we try to study the hypergraph, we can say, okay, the homology is given by either this one or another. Then if we want to look more, we can look at gap. So this is our gap. Okay, so then that's actually the ideas we try to produce the homology. Then there are some words we have to dig down further. So okay, so now look at hypergraph. Then we try to look at like Laplacian, discrete Laplacian, discrete Morse theory, Pope theory, and persistent homology of this type. So try to get some folklore like this, some people's ideas, the topological data analysis, which I work on that. So I think lots of interesting things I try to explain to you, on this hypergraph. Okay, so I now explain a little bit about topological because of timing. So I just shortly to say, there's a topological data that's persistent in the homology, basic ideas. Okay, so persistent homology will give us there will be supposed to be some finite subset inside the Euclidean space. So this is called a pointed cloud data. And then you can look at the balls of radius I centered each point. And then if they are they're intersecting, okay, so if you balls, three balls intersecting together, we get two superstacks. No, four balls intersecting together, we get three superstacks. So or we get one construction there, we get a pictorial Rie complex. Also, there's another way to construct a Chern complex, right? And the relation between these, I just say the view. Okay, so this is the pointed cloud data. Okay, so we take the radius. The radius will be the persistent. Okay, so actually you can take a graph. So if you have 2 points, 2 balls joined together, you can graph. Now you can construct some graph theory. You can construct some complex. Just to look at the complete subgraph. Okay, so now in topology you get the polynomial that comes from this bridge complex. Then you get the chain complexes. Then this is something persistent homology, to apply. Okay. So now actually we did a several work I just mentioned it over. So one thing we try to do is to look at the weighted simplification complex and. Let's get back to here. We try to say, oh, that maybe your data has some weight, not balance. So some point will be more important than another, maybe less important than another. Let's try to play games on weighted situation. Try to make some weighted, and also. Did something like, okay, so I simply got timing, so try to say a little bit, just follow this idea. You can define the weighted homology, and we make, and also we also try to work on the persistent homology and discrete Morse theory for hypergraph, and more recently, I think 2 months ago, Jelena Grönig and I also try to. I think we're almost done, but we're still writing. We also find some uniform topological approach in data science. That means currently data science, the percent of models only suitable for pointed ground data. Actually, we can also to approach it for graphical data as well. So then give some uniform topological tool. And but anyway, these are the kind of things we try to first set up some mathematical notions, extend the common notion, and then later on, I think it's quite related later, this discrete Morse theory will be one of the essential tools to play with the application. Yeah, I think I should stop here. Okay, thank you.
Thank the speaker for a nice lecture.
Can you see
Okay,
us?
yeah, let me try to do. Okay, yes.
Can you
Can you
see
see it now? Yes.
You see
Yeah.
us also?
Okay, yeah. Okay.
Maybe
Yeah.
there are some questions for this time. Okay.
There are no questions, so thank you, speaker, again.
Okay.